Good morning, everyone. Today, we will discuss the experiment on separation of hysteresis and eddy current losses in single-phase transformer. So, the aim of the experiment is to separate the hysteresis and eddy current losses from iron loss of a single-phase transformer. So, for this, we require some apparatus. So, that is transformer of 1 kVA rating, single-phase supply. So that is required quantity is 1. Some connecting wires are required, and voltmeter, that is 0 to 300 volt, moving iron type, that is 1. Ammeter, there are 2 ammeters are required. One is AC ammeter, another one is DC ammeter, moving iron and moving coil, 0 to 10 bar 20 amps, and another one is 0 to 2 amps. This is for armature connection, that is 1. And watt meter, so that is 10 amps 600 volt, that is low power factor, because we are connecting the transformer in open circuit, so we are not connecting any load. Okay, so and rheostats, so there are 2 rheostats are required. 750 ohm is one, and another one is 38 ohm rheostat. So these things, and tachometer, so digital tachometer is required for the speed measurement. Okay, and the circuit diagram, this is the circuit diagram of separation of hysteresis and eddy current losses in a single phase transformer. So this is the transformer. Secondary is open circuited. In primary side, we need to connect all the meters. So one is voltmeter, ammeter, and wattmeter. Voltmeter 0 to 300 volt connected in parallel with the supply, and this is the ammeter 0 to 2 amps, that is moving iron type, so connected in series, and wattmeter, so that is 2 amps 300 volt LPF, low power factor. So in our experiment we have multifunction meter. Instead of connecting all the 3 meters, so we will connect a multifunction meter in the primary side of the transformer. Okay, so how to conduct the separation of hysteresis and eddy current loss that can be derived from iron losses. So for that purpose, we require a variable frequency, so that can be achieved by the 2 arrangements, that is motor and alternator arrangement. So this, in this alternator, we have 3-phase supply is there. Instead of 3-phase supply, we will take any one phase. One is R phase and another one is neutral, that should be connected to the transformer side. And the DC motor is coupled with the alternator. So the DC motor connection, that through the 3-point starter. So L is for line, F means field, A means armature. Okay, so these connections are to be made. Okay, so that is DC supply of 220 volt should be given through the 3-point starter. So that is connected through the mains, that is the line is connected to the main supply, and from the field it will be connected to the field rheostat of 750 ohm, then connected to Z and ZZ terminals of the coils, that is connected in parallel, that is the shunt connection. And another one is armature. So A, that is A terminal is connected to the 38 ohm rheostat. From that it is connected to point A and AA of the motor armature. So this is the DC shunt motor circuit. And another field winding connection of alternator. So this is the alternator connection. Output terminals R phase, Y phase, B phase, and neutral is there. Apart from this, so to build up the voltage, we require DC supply, that should be excitation is given to the poles to become an electromagnet in the alternator. So for that purpose, this is the alternator field, that is F and FF, that can be connected, that can be given the DC supply, separate excitation that has to be given. Again, same 220 volt, that is given through the rheostat and field coil F and FF. Then it is connected to the ammeter 0 to 2 amps. Okay, then connected back to the supply. So this is the circuit diagram of separation of hysteresis and eddy current losses in single phase transformer. So observation table. So in the observation table, so the serial numbers, speed of the prime mover, that is N in RPM, frequency in hertz, primary voltage V in volts, wattmeter reading, and wattmeter reading divided by frequency, that is called as Wi by F, and voltage reading divided by frequency, that is called as V by F. These to be noted. So for that purpose, for first reading, suppose 1500 rpm. So for 1500 rpm, so that is called as 50 hertz, that is a 4-pole machine. So you will get a 50 hertz. So that can be calculated, the speed can be calculated for the corresponding frequency. So for 50 hertz, so next is 47.5 hertz. Okay, and next reading you have to take for 45 hertz, and similarly 42.5 hertz, in decreasing order, and 40 hertz. Okay, so for 50 hertz, that is 1500 rpm, because your n is equal to 120 f by p, 120 f divided by p. So you take number of poles is equal to 4, number of poles is equal to 4, 120, and corresponding frequency is 50 hertz. So calculate it, you will get 1500 rpm, right? So similarly, for 47.5 hertz, you calculate the speed. So you will get 1425 rpm. Similarly, you calculate for 45 hertz. So that is 1350 rpm. Similarly, you calculate 42.5 hertz, you will get, according to the formula, 1275 rpm. And lastly, for 40 hertz, you will get 1200 rpm. Okay, so first you note all these things. According to this, you apply the speed of the machine, and corresponding frequency can be matched. Okay, for this particular 1550 hertz, you check the primary voltage level. So nearly it is 220 volts. Okay, you will get some 220 or 224 volts. You will get, so corresponding wattmeter reading. So that can be, will get in terms of 30 watts, 34 watts, 35 watts, like that. So note down all the readings from the voltmeter, ammeter, and wattmeter reading from the multifunction meter. Okay, so this is the observation table. So if you connect wattmeter separately, you need to calculate the wattmeter constant, voltage range into current range into power factor by full scale deflection of the meter. So iron losses, this is the total iron losses. This consists of hysteresis loss as well as eddy current loss. So these iron losses are obtained from the wattmeter. So wattmeter reading will get total iron losses. So we need to separate total iron losses in terms of hysteresis as well as eddy current. So we'll make the arrangement through this graph. So this nature of graph, so this will shows the x-axis and y-axis. In the x-axis, we have to plot the frequency. Okay, so right, the x-axis, these are the frequency, and in y-axis, you have to note Wi by f. Okay, so whatever the Wi is there, Wi by f, you have calculated in this table corresponding for all the 5 readings. You draw Wi by f. So once you draw Wi by f versus f, so you will get a straight line. Okay, so after this, you need to calculate slope, the corresponding this. So that is delta Wi by f. You take any 2 reading, okay, you will get delta Wi by f, and similarly you take 2 frequency. Okay, so 2 points of the frequency, corresponding frequency, so you will get delta f. Okay, so you calculate, this is called as a, so where it is started, this is called as a part, and we need to find out B part. So B is equal to delta Wi by F. So this one divided by delta F, this one. So whatever the distance from here to here, that is called as delta Wi by F. So write the value of delta Wi by F. Similarly divided by the, you write this value that is called as delta F. Okay, so you will get A value as well as B value. Okay, once you know the A value and B value, so you can calculate the hysteresis and eddy current law. So for frequency, so Pn by 120. So similarly, P is the number of poles, N is the synchronous speed in RPM. For hysteresis loss, WH, that is called as WH is called as hysteresis law, that is given by A into F. So we have A reading here to here. So multiply by your corresponding frequency. Okay, A into F, this will give the hysteresis loss. So, and similarly, eddy current loss that can be calculated by WE is equal to B into F square. So you calculated the B. So according to the B multiplied by F square. So this F that can be taken for any reading. Okay, any reading, either 50 hertz, 47 hertz. So for any reading, so corresponding wattmeter reading that can be divided here for hysteresis as well as eddy current loss. Okay, finally we will get iron loss or core loss is equal to Wi is equal to WE plus WH. WE means that is eddy current loss. WH is called as hysteresis loss. These are the calculation you need to do in this experiment. Okay, so and for theoretically the Steinman's formula WH is equal to neta into Bm raised to 1.6 into F into V watts. So this is the equations in the theory part, and similarly the eddy current loss, the equation for eddy current loss theoretically, that is the Ke into Bm square F square T square into V, that is in terms of watts. Okay, so T is the thickness of the lamination, Bm is the maximum value of the flux density in Weber per meter square, V is the volume of magnetic material in meter cube. Okay, so finally Wi is given by K1 into F plus K2 into F square, or Wi by F is equal to K1 plus K2 into F. Okay, so these are the theoretical part of the experiment and how to conduct the experiment. That is the procedure. So connections are made as per the circuit diagram. So according to the circuit diagram, we have three components, that is three devices are there. One is DC motor, another one is alternator, third one is transformer. We need to connect the DC motor part connection, similarly alternator part connection, as well as third one is transformer connection. So or have to do the connection as per the circuit diagram. And before switch on the supply, the prime mover is started with the 3-point starter, a DC starter that can be DC motor can be started through the 3-point starter and for the rated speed. Okay, and adjust the rheostat. So previously the armature rheostat should be in the cut-in position and field rheostat should be in the cutout position. Okay, according to that, you need to vary the rheostat first. You need to vary the armature rheostat. After that, we need to vary the field rheostat for the rated voltage applied, that is rated speed will be applied, that is 1500 rpm. After that, by adjusting the speed of the prime mover by varying the field rheostat, the required frequency is obtained and corresponding reading are noted. Okay, the frequencies that can be calculated. So for 50 hertz, what is the speed? So corresponding speed that is available in the observation table. According to that, you adjust the speed and match the frequency and uh, note down the wattmeter reading and voltmeter reading. Okay, the experiment is repeated for different frequency and corresponding readings of the are tabulated. And prime mover is switched off after completing the experiment. So prime mover is switched off using DPIC switch. So after bringing all the rheostat in initial position. Okay. So in the beginning, how the rheostat in cut in and cut out position, that is of armature and field rheostat, you keep as it is. okay, and switch on the main TP, okay, main supply. So after that, from the tabulated readings, the iron loss is separated from eddy current loss and hysteresis loss by using respective formula. So this is the procedure how to do the experiment. And some of the pre-lab questions and post-lab questions are there. So answer for these questions, okay, and finally you will get the results. And the hysteresis and eddy current losses are separated from iron loss of a single phase transformer. So this is the experiment. So we will do the demonstration experiment in the next class. Thank you very much.